I welcome you back to Analytics Simplified. Now we are creating a new series on algorithms analysis and design, and in this series we are presenting the first chapter, that is Master's Theorem. Okay, so we will be going with this Master's Theorem in this lecture, and then we will also be solving some problems. Okay, so when it comes to Master's Theorem, what is Master's Theorem? So you already know that Master's Theorem is basically used to find out the time complexity of a recurrence relation. The thing that needs to be noted is that not all recurrence equations can be solved by using Master's theorem. Okay, so only those recurrence equations can be solved by Master's theorem that can be written in this form. That means which can the recurrence equations that can be written in the form a times t of n by b plus theta of n to the power k log n raised to the power p. Okay, so all the recurrence equations that can be written in this particular form, and for which the coefficients a b p and k satisfy these constraints, only those recurrence equations can be solved by using the Master's theorem. So in this equation, n is the size of the input. Okay, a, B, K, and P are the coefficients, and these constraints have to be followed by these coefficients for a problem to be solved by Master's theorem. Okay, so what I will do is I will present you with a series of steps that you have to follow in order to solve a problem by using Master's theorem. Okay, so let us talk about the different steps. So when it comes to step one, so what we have to do in step one is whatever recurrence equation is given to you, you have to simply write it in the form as equation one. So whatever recurrence equation is given to you, you have to simply try to put this in this standard form. Okay, this is my standard form, so the recurrence equation needs to be written in this standard form. Okay, this is my step one. What we have to do in step 2, in step 2 you have to identify the values for a, b, k, and p. Note that after step 1 the equation is in this standard form, so simply by comparison you can get the values for these coefficients a, b, k, and p. Okay, so this is my step 2. So once you have obtained the values of a, b, k, and p, we now move to step 3. So what we are supposed to do in step 3, in step 3 we are supposed to find out if the values for a, b, k, and p satisfy the constraints. That means you have to check if a is greater than equal to 1, you have to check if a is greater, if b is greater than 1, if k is greater than equal to 0, and if p is a real number. Okay, so these four checks have to be applied on the values for a, b, k, and p. And if you find out that okay, all the four constraints are satisfied by all these values, then you say that okay, now your problem can be solved by using Master's theorem. Okay, so when you actually go for solving the problem with Master's theorem, the first thing that you have to do is now you have to compare the value of a with b raised to the power k. See, you already know the value of a, you already know the values for b and k. Okay, so you have to first compute b raised to the power k, and you have to already have the value of a. You have to simply compare these two values. Okay, so when you compare these two values, three cases arise. In the first case, you can have value of a greater than b raised to the power k. In another case, you can have the value of a as equal to b raised to the power k, and in the third case you can get the value of a to be less than b raised to the power k. Okay, so these are the three different cases corresponding to the relationship between a and b raised to the power k. So let us start with the first case. The your problem is in case 1 when the value of a is greater than b raised to the power k. So once you notice that the value of a is greater than b raised to the power k, you say that the problem belongs to case 1. And in this case, the time complexity assumes a very simple form, that is theta of n raised to the power log a base p. Okay, so you already have the values for a and b, so you can compute this quantity. Okay, this quantity can always be computed because a and b are known to you. Now you simply have to put the complexity in this form. So theta of n raised to the power whatever this number comes, this actually turns out to be your time complexity. Now this is when the value of a is greater than b raised to the power k. Okay, so this is the solution for case 1 when your problem is in case 1. Okay, so in case 2 what will happen is case 2 will arise when the value of a, when you compare the values for of a with b raised to the power k, and if they come out to be equal, we see that the problem is in case 2. So in this case what we are going to do is now we are going to observe the value for p. So again three cases will arise. P could be less than minus 1, P could be equal to minus 1, and P could be greater than minus 1 also. Okay, so corresponding to these three different settings for value of P, we will have different subcases, and we will also be having different solutions. So if P is less than minus 1, the time complexity will take the form theta of n raised to the power log a base b. Okay, this is only when the value of a is equal to b raised to the power k and p value is also less than minus 1. Okay, this is the first subcase. In the second subcase, what can happen is that the value of a is equal to b raised to the power k. That means we are still operating in case 2, and value of p turns out to be equal to minus 1. In this case, the time complexity for the recurrence relation could be given by n raised to the power log a base b multiplied by log n whole square. Okay, so this is the time complexity when you are in case 2 and the value of p turns out to be equal to minus 1. In the third case, when p is greater than minus 1, this is going to be your form. This is going to be the time complexity n raised to the power log a base b multiplied by log n raised to the power p plus 1. That means log n raised to the power, you already know the value of p, so this is the last term. Okay, I have written for simplicity. Log n you have to compute, and the entire value has to be raised to the power p plus 1. So these are the three different settings corresponding to what value p assumes when you are in case 2, and corresponding to each of these three settings you will be having different values for the time complexity. Okay, so in case you want, you can pause this video and you can write down on the notebook, so that when we will be solving the problems, it becomes easy for you to follow. Okay, now these are the two cases we have discussed: one when the value of a was greater than b raised to the power k, and another when the value of b was equal to a. Okay, now we are going to talk about the third case. In the third case, what will happen is a is less than b. Okay, so once you compare the value of a with b raised to the power k, and if you find out that the value of a is less than b raised to the power k, we say that the problem is in case 3. Okay, so when the problem is in case 3, again we are going to observe the value for p, and we will have two different subcases. Okay, so in one, value of p could be less than 0, and in another subcase the value of p could be greater than or equal to 0. Okay, so when the value of p is less than 0, the time complexity for the recurrence equation can be given as big O of n raised to the power k. You already know the value of k, right? And once you find out that the value of a is less than b raised to the power k, that means the problem is in case 3 and value of p is less than 0. So simply you can write the time complexity as Tn is equal to big of nk. And in case the value of p is greater than or equal to 0, in this case the time complexity for the recurrence equation becomes theta of n raised to the power k multiplied by log n raised to the power p. Okay, so you can just note down these values and the different settings corresponding to which you are getting different values for the time complexity. Okay, and then in the next lecture I will be taking some problems. At least I will try to cover as many problems as possible. So once you have these handwritten notes with you, it will become very easy for you to follow. Okay, so I will stop here. Okay, and in the next video we will be practicing some problems on master's theorem.